Welcome to General Chemistry Chapter 1. We will be discussing methods and measurements in this chapter. The first thing we will look at is the discovery process. Chemistry is the study of matter, and matter is anything that has mass and occupies space. Its chemical and physical properties, the chemical and physical changes it undergoes, and the energy changes that accompany those processes. We are going to define energy as the ability to do work to accomplish some change. Now, if we look at the major areas of chemistry, we see that there's biochemistry, which is the study of life at the molecular level, organic chemistry, which is the study of matter containing carbon and hydrogen, inorganic chemistry, which is the study of matter containing elements which are not organic, analytical chemistry, which is to analyze matter to determine the identity and composition, and physical chemistry, which attempts to explain the way matter behaves. As you can see, chemistry has several applications to all the things around us, including public health, medical practitioners, the pharmaceutical industry, food science, forensic sciences, as well as many other. Now, looking at the scientific method, we see that the scientific method is a systematic approach to the discovery of new information. Characteristics of the scientific method are as follows. There's observation and experimentation. There's the formulation of a question, a pattern of recognition, developing theories, followed by the summarizing of information. The diagram below lists the process of the scientific method. Now, if we look at the use of models in chemistry, we see that they can aid in the understanding of the chemical unit or system. Again, a model is often used for this understanding, and good models are based on everyday experience. To the right, you'll see a picture of the ball and stick methane model, where the color code is for the balls and sticks show the attractive forces holding the atoms together. Moving on to matter and properties, we see that properties are characteristics of matter, and again, they're both chemical and physical. If we look at data, it's the individual result of a single measurement, and results are the outcome of an experiment. Next, looking at the three states of matter, we see that there is gas, where particles are widely separated, and there is no definite shape or volume. There's also liquid, where the particles are closer together, but there is a definite volume, but no definite shape. And finally, there's solids, which the particles are very close together, and there's a definite shape and a definite volume. These are examples of the three states of matter for water, where the solid would be ice, the liquid would be water, and the gas would be steam or vapor. In this diagram below, you can see the comparison of the physical states of matter. Now, if we discuss physical properties, these are observed without the changing of composition or identity of the substance. There can be a conversion from one physical state to another. Now, a physical change produces a recognizable difference in the appearance of a substance without causing any change in its composition or identity. For example, this would involve the melting of an ice cube, where it would go from a solid ice to a liquid water. In the diagram below, we can see that the separation can occur by physical properties, where the magnetic iron is separated from other non-magnetic substances such as sand. This property is used as a large-scale process in the recycling industry. Now, looking at chemical properties, a chemical property is a result in a change in the composition and can be observed only through a chemical reaction. A chemical reaction, which involves chemical change, is a process of rearranging, removing, replacing, or adding atoms to produce new substances. In this equation, we have reactants, in this case hydrogen and water, which combine to form water, which is a product in this chemical reaction. In order to test your understanding of chemical and physical properties, please classify the following as either a chemical or physical property: color, flammability, hardness, odor, and taste. Also, Please try to classify the following as either a chemical or physical change. Boiling water becomes steam, butter turns rancid, the burning of wood, mountain snow peak melting in the spring, or the decay of leaves in winter. Now there's also intensive properties, which is a property of matter that is independent of the quantity of the substance, such as density or specific gravity. In addition, matter also has extensive properties, which is a property of matter that depends on the quantity of the substance, such as mass or volume. Now when we're looking at the classification of matter, we can see that we can either have a pure substance, which is a substance that only has one component, or a mixture, which is a combination of two or more pure substances in which each substance retains its own identity, not undergoing a chemical reaction. Continuing with the classification of matter, we can also look at a pure substance, which can be broken into an element, which is a pure substance that cannot be changed into a simpler form of matter by any chemical reaction. Or we have compounds, which is a substance resulting from the combination of two or more elements in a definite reproducible way in a fixed ratio. Now looking more at the classification of matter in relation to a mixture, again, a mixture is a combination of two or more pure substances in which each substance retains its own identity. However, within mixtures, there's a homogeneous mixture, which is a uniform composition where particles are well mixed and thoroughly intermingled. And there's also a heterogeneous mixture, which is non-uniform composition and random placement. Now looking at significant figures in scientific notation, we see that the information-bearing digits or figures in a number are called the significant figures. Significant figures are all the digits in a number representing data or results that are known with certainty plus one uncertain digit. The measuring device used determines the number of significant figures as a measurement has. Also, the amount of uncertainty associated with the measurement is indicated by the number of digits or figures used to represent the information. Now, if we look at the recognition of significant figures, we see that all non-zero digits are significant. We see that in the number 7.314, it has 4 significant digits. Also, the number of significant digits is independent of the position of the decimal point. So 73.14 also has 4 significant digits. Finally, zeros located between non-zero digits are significant as well. So 60.052 has 5 significant digits. Now looking more specifically at the use of zeros in significant figures, we see that zeros at the end of a number, trailing zeros, are significant if the number contains a decimal point. So for example, 4.70 has 3 significant digits. Looking at trailing zeros, however, they are insignificant if the number does not contain a decimal point. So 100 has 1 significant digit, while 100 point has 3. Finally, zeros to the left of the first non-zero integer are not significant. So 0.0032 only has 2 significant digits. To test your understanding, please try to answer how many significant figures are in the following numbers: 3.400, 3004, 300 point, and 0.003040. Now moving on to scientific notation, this is used to express very large or very small numbers easily and with the correct number of significant figures. What happens is we are representing a number as a power of 10. So for example, 4,300 is equal to 4.3 times 1,000, which is equal to 4.3 times 10 to the third. Now in order to convert a number greater than 1 to a scientific notation, the original decimal point is moved x places to the left, and the resulting number is multiplied by 10 to the x. So the exponent x is a positive number equal to the number of places the decimal point was moved. So for the example 5,340, it is equal to 5.34 times 10 to the third. If we ask the question, what if you want to show the above number has 4 significant figures? It would be equal to 5.340 times 10 to the third. Now, to convert a number less than 1 to scientific notation, the original decimal point is moved x places to the right, and the resulting number is multiplied by 10 to the negative x. The exponent x is a negative number equal to the number of decimal places the point was moved. So for the number 0.0534, that would be equal to 5.34 times 10 to the negative 2. Now, when we look at types of uncertainty, we first can see error, which is the difference between the true value and our estimation. This can either be random or systematic. There's also accuracy, which is the degree of the agreement between the true value and the measured value. And then we also have precision, which is a measure of the agreement between the replication of measurements. Now, looking at significant figures in calculation of results, we first want to look at the rules of addition and subtraction. This is the result in a calculation which cannot have a greater significant figure than any of the quantities that produce that result. Consider this: 37.68 liters plus 6.71862 liters plus 108.428 liters would be equal to 152.82662 liters, but the correct answer is actually 152.83 liters based on the rules for addition and subtraction for significant figures. Now, if we look at the rules for multiplication and division, the answer can be no more precise than the least precise number from which the answer is derived. And the least precise number is the one with the fewest significant figures. Also, if we look at exact and inexact numbers, we see that inexact numbers have uncertainty by definition, while exact numbers are a consequence of counting. A set of counted items, such as beakers on a shelf, has no uncertainty. The exact numbers, by definition, have an infinite number of significant figures. Now, if we look at the rules for rounding off numbers, we see that when the number to be dropped is less than 5, the preceding number is not changed. However, when the number to be dropped is 5 or greater, the preceding number is increased by 1 unit. So when rounding the following number to 3 significant figures, we look at 3.34966 times 10 to the fourth. We see that the number being rounded is actually 3.35, where it was rounded up to 5 from 4, times 10 to the fourth. To practice your understanding of this, please attempt to round off each number to 3 significant figures. 1, 61.40, 2, 6.171, and 3, 0.066494. Now, looking at units and unit conversion, we see that units are the basic quantity of mass, volume, or whatever quantity is being measured. A measurement is useless without its units. In the English system, we have a collection of functionally unrelated units, which makes it difficult to convert from one unit to the other. For example, 1 foot is equal to 12 inches, which is equal to 0.33 yards, which is equal to 1 over 5,280 miles. However, the metric system is composed of a set of units that are related to each other decimally and systematically. These units relate by powers of 10. So when we look at the basic unit of the metric system, we see that a mass is equal to a gram and represented as G, that length is equal to meters, which is represented as M, and that volume is equal to liters, which is represented as L. These basic units are the units of a quantity without any metric prefix. Now in this chart, we can look at all of the units and prefixes of the metric system. Now, unit conversion. You must be able to convert between units. both within the metric system and between the English and metric system. The method used for conversion is called the factor label method or dimensional analysis. I want to express that this is going to be extremely important, so please understand unit conversion, in particular between the English system and the metric system. Alright, so let your units do the work for you by simply memorizing the connection between units. For example, how many donuts are in 1 dozen? We say that 12 donuts are in a dozen, so 12 donuts is equal to 1 dozen donuts. Why does any number divided by itself equal? It equals 1. Now this fraction is called a unit factor. What does any number times 1 equal? Well, it equals that number. So the multiplication by a unit factor does not change the amount, only the unit. We use these two mathematical facts to use the factor label method. A number divided by itself is equal to 1, and any number times 1 gives that number back. So for example, how many donuts are in 3.5 dozen? You can probably do this in your head, but try using the factor label method. Now if we start with the given information, we see that 3.5 dozen times 12 donuts over 1 dozen is equal to 42 donuts. Then we set up your unit factors, and we see that the units cancel. Then we multiply and divide by all the numbers. Now the common English system units are listed below for weight, length, and volume. Try to convert 12 gallons to units of quarts as an example of your understanding this conversion. There's also intersystem conversion units, where we would see going between mass from English to metric, length from English to metric, and volume from English to metric. So try to convert 4.00 ounces to kilograms. To practice additional unit conversions, please try the following 3 problems. Convert 5.5 inches to milliliters, convert 50.0 milliliters to pints, and convert 1.8 inches squared to centimeters squared. Now looking at experimental quantities, we first see that mass is the quantity of matter in an object, but this is not synonymous with weight. And if we remember back, the standard unit is the gram. But if we look at weight, this is going to be equal times the mass times acceleration due to the gravity. So mass must be measured on a balance, not a scale. Now units should be chosen to suit the quantity being described. So for example, a dump truck is measured in tons, a person is measured in kilograms or pounds, a paperclip is measured in grams or ounces, but what about an atom? For atoms we use the anatomic mass unit, which one anatomic mass unit is equal to 1.661 times 10 to the negative 24th grams. Now when we look at length, we know that this is the distance between 2 points. The standard unit, like we mentioned before, is the meter, and long distance are measured in kilometers. So the distance between atoms are measured in nanometers, which is equal to 10 to the negative 9th meters. Now for volume, it's the space occupied by an object, and the standard unit is the liter, like we mentioned. The liter is the volume occupied by 100 grams of water at 4 degrees Celsius. So 1 milliliter is equal to 1/1000th of a liter, which is equal to 1 centimeter cubed. The following diagram represents 1 milliliter and the cubic centimeter and shows that they are equivalent. Now if we look at time, the metric unit is the second, and temperature is the degree of quote-unquote hotness of an object. Now if we look at conversion between temperature, in particular Fahrenheit and Celsius, we see the following equations. Look at the equations and attempt to convert 75 degrees Celsius to Fahrenheit and convert negative 10 degrees Fahrenheit to Celsius. Now there's also a temperature scale called Kelvin. The Kelvin scale is another temperature scale. It is of particular importance because it is directly related to molecular motion. As molecular speed increases, the Kelvin temperature proportionately increases as well. Now moving on to energy, again, energy is the ability to do work. There are two types of energy that we want to discuss. One is kinetic energy, which is the energy of motion, and potential energy, which is the energy of position and or described as stored energy. Energy can also be categorized by form, which would include light, heat, electrical, mechanical, and chemical. Now, if we look at the characteristics of energy, we see that energy cannot be created or destroyed, energy may be converted from one form to another, that energy conversion always occurs with less than 100% efficiency, and that all chemical reactions involve either a gain or loss of energy. Now, the units of energy as follows. There's basic units, which are a calorie or a joule. So 1 calorie is actually equal to 4.184 joules. A kilocalorie, also known as the large calorie, is the same calorie as food calories. So 1 kilocalorie is equal to 1 calorie with a large C for food calories, which is equal to 1,000 small c calories, which is the basic unit of energy. So 1 calorie with the small c is the amount of heat energy required to increase the temperature of 1 gram of water 1 degree Celsius. Now looking at concentration, we see that concentration is the number of particles of a substance with the mass of those particles that are contained in a specified volume. Concentration is often used to represent the mixtures of different substances. So the concentration of oxygen in the air, the pollen counts, or the proper dose of an antibiotic. Now looking at density and specific gravity, we will talk about density, which is the ratio of mass to volume. Again, this is an extensive property, and density is used to characterize a substance as each substance has a unique density. The units for density include grams per milliliter, grams per centimeter cubed, and grams per cc, where in the equation we see the density would be mass over volume, or m over v. Here's a picture showing the densities of different things. For example, water and liquid mercury have different densities, so water sits on top of a more dense liquid mercury. We also see objects like a cork and a brass nut, where the cork is less dense than water, so it floats, but the brass nut is more dense than water, so it sinks. The following chart shows the density of some common materials that you can examine. Now, if we look at calculating the density of a solid, we would have 2.00 centimeters cubed of aluminum, which are found to weigh approximately 5.40 grams. If we calculate the density of aluminum in units of grams per centimeter cubed, we would use the formula. And we would substitute our values of 5.40 grams over 2.00 centimeters cubed. This would give us a density for the aluminum of 2.7 grams per centimeter cubed. Now to practice our density calculations, please attempt to answer the following questions. For air, which has a density of 0.0013 grams per milliliter, what is the mass of a 6.0 liter sample of air? Next, calculate the mass in grams of 10 milliliters of mercury if the density of mercury is 13.6 grams per milliliter. And finally, calculate the volume in milliliters of a liquid that has a density of 1.20 grams per milliliter and a mass of 5.00 grams. Finally, addressing specific gravity, the values of density are often related to a standard. Specific gravity is the ratio of the density of the object in question to the density of pure water at 4 degrees Celsius. So specific gravity is a unitless term where the two units cancel. And often, the health industry uses specific gravity to test the urine and blood samples. So again, specific gravity is equal to the density of an object in grams per milliliter over the density of water in grams per milliliter. This concludes Chapter 1, which is the chemistry looking at methods and measurements. As you can tell, there's a lot of terms and units and conversions and calculations that needs to be practiced. So please take the time to make sure that you understand the conversions and the calculations. Feel free to email me at any time with questions.